Hello everyone, my name's Dr. Vile and welcome to my A Level Chemistry YouTube channel. The purpose of this is all about getting you ready for your A Level Chemistry exams, and with that in mind, the purpose of this video is going to be all about calorimetry, which is about how we measure enthalpy changes for chemical reactions practically in the lab. So that's what we're going to be focusing on this video. If you find it helpful, please like, please share, please subscribe and keep checking back to the channel for more content. So I want to start by explaining what a calorimeter is, and I've just included a diagram on the screen of a really basic calorimeter. It's basically a plastic or a polystyrene cup inside an insulated container, ideally with a lid on the top, and then you have a thermometer going into the reaction vessel, and you have a stirrer so that you can stir the reaction. And what happens is you carry out the reaction inside the polystyrene cup, and a temperature change will occur depending on whether the reaction is exothermic or endothermic, and your thermometer will measure the temperature change within the vessel. So you take readings and you're constantly stirring to make sure that the reaction is complete, and it's inside a polystyrene cup with a lid on the top so that the system is insulated to make sure that as little possible heat escapes to the surroundings. And what we're going to look at is how we do calculations from a calorimeter to work out the enthalpy change. And with that in mind, there are some formulae that we need to know. So we need to know how to calculate the energy change that is associated with the reaction. So E, which stands for energy, and it's measured in joules, is equal to M times C times delta T. And I'm going to go through what each of these terms and what it means. So M stands for the mass of the water that the thermometer is in. So the thermometer will be in the vessel and it's the mass of the water, and it's measured in grams. Delta T is the temperature change. So to calculate the temperature change, you need to know the initial temperature and you need to know the final temperature. Now the temperature change is technically in Kelvin. However, in the lab, you measure the temperature in degrees Celsius. However, because we're dealing with a temperature change, say it goes up by 10 degrees Celsius, because of the way we calculate Kelvin, the temperature change in Kelvin would be exactly the same. So if it goes up by 10 degrees Celsius, that's the same as a plus 10 degrees Kelvin. So we're quite happy to use degrees Celsius for the temperature change and then allow it for Kelvin. And then lastly, C is the specific heat capacity of water. And I'm going to explain what that means in a second. So specific heat capacity of water, it is a constant and it is 4.18 joules per gram per Kelvin. So hopefully you can see how the units line up. You've got grams for mass and grams to the -1, so they cancel out. You've got Kelvin for the temperature change and Kelvin for the -1 in the specific heat capacity, so that cancels out, which means that energy is therefore just measured in joules. Now the specific heat capacity of water is the amount of energy in joules that is required to heat 1 gram of a substance by 1 Kelvin. And as I say, it is a constant that you can look up on your data sheet. So you've got the mass of water that the thermometer is in, you've got the specific heat capacity of the water, and you've got the temperature change of the water. So you need to know your initial temperature and your final temperature. Once you've calculated your energy change in joules, the most common thing that we have to do is convert it into kilojoules. So we'd need to divide that by 1,000. And what we're interested in eventually is how we calculate the enthalpy change for the reaction, delta H. So if this is energy, E, enthalpy is delta H. And the way we do this is it's minus delta E. So whatever your energy change is, this is delta E, should be a delta sign there, minus delta E divided by N, which is the number of moles of the chemical that is reacting. And N is calculated by mass divided by molecular mass. So with this in mind, I want to look at a very specific example. I'm going to work through the lab book exercise that you will have done in class if you're doing the WJEC course. So the practical is all about an indirect determination of an enthalpy change. And I'm going to go through the specific example. It doesn't matter if you're watching this video and you're doing a different course. Hopefully the principles of it will be pretty similar. So we'll go through it with some specific numbers. So if you're doing WJEC, it is this practical here in your lab book, which is the indirect determination of an enthalpy change of reaction. And basically what it is that you have the reaction of magnesium oxide and carbon dioxide, CO2, to form magnesium carbonate. And this is a reaction that is very difficult to measure the enthalpy change for directly, so we could just call this delta HR. We can't measure it directly, but what we can do is measure it indirectly. So what we can do is react magnesium oxide with acid, and we can react magnesium carbonate with acid to work out the neutralization products. So you take some magnesium oxide, react it with acid, measure the enthalpy change. So we could just call this arrow 1. And you could take the magnesium carbonate, react it with the acid, work out the enthalpy change, and call this arrow 2. And therefore delta HR would equal arrow 1 minus arrow 2, because you're going against the second arrow, so it's minus. So we're going to work out two different enthalpy changes, arrow 1 and arrow 2, and then plug them into our Hess cycle to work out delta HR. So to do this, practically in the lab, at some point I'll put together a video actually showing some of these practicals in the lab itself. This video is just going to be focused on the calculations for now, but I might put together another video soon looking at the practical ways that this is done. You need a digital balance, thermometer, a calorimeter, which is just your two polystyrene cups inside each other, pipette with filler, stopwatch, spatula, weighing boat, and then access to hydrochloric acid, magnesium oxide, and magnesium carbonate. I'm not going to go through the method in great detail now, it's shown on the screen, but basically what you're doing is you start off by weighing out 0.9 grams of magnesium oxide, and you also measure out 50 centimeters cubed of hydrochloric acid into your calorimeter. And what you're going to do is measure the temperature of the hydrochloric acid over time, so it might just stay pretty steady, and then you're going to add the magnesium oxide, and suddenly the temperature is going to fly up, and then it will gradually start coming back down again. And we can work out delta T, which is on the next page. I'll show you how to do that. Okay, and then you repeat again for the magnesium carbonate using 3.5 grams of magnesium carbonate. So if you want, take some time now to read the method, but I'm going to go on to what we do with the data at this stage. So for magnesium oxide, you can see a graph on the screen at the moment. If you follow along here, I'll grab a highlighter pen so I can annotate my graph. I measured the temperature of the hydrochloric acid. I'm just trying to highlight this in yellow here. And I've measured it for the first, well, what was it, 120 seconds, and you can see it's pretty stable. Then at 150 seconds, I added my hydrochloric acid, I added the magnesium oxide into the hydrochloric acid, and you can see the temperature started to rise, it then kept on rising, and then flattened out, and then the temperature started to drop off over time. So to work out delta T, what you do is you take your cooling line here and you extrapolate back to the time of mixing, which would have been, in this case, would have been about 180 seconds. So you extrapolate back to the time of mixing. I think that's an anomalous result there. And T2 was 37.6 degrees. I used a thermometer that's accurate to 0.2 of a degree Celsius for this. And then for the initial temperature, you extrapolate to 180 seconds, and you can see the temperature was 22 degrees Celsius. So you've got an initial temperature of 22 and a maximum temperature of 37.6, and therefore you've got delta T, which is 15.6 degrees Celsius, and it's gone up by 15.6 Celsius for the magnesium oxide. So you're taking temperature measurements every 30 seconds, then you mix the chemicals, and you just keep recording the temperature over time, and then you extrapolate your lines back to the time of mixing. For the magnesium carbonate, I've done exactly the same thing. As you can see here, I've measured the temperature initially, then I mixed the chemicals, the temperature shot up, and then I've let it cool down and extrapolated back to the time of mixing, which is 180 seconds. My initial temperature was 21.8, my final temperature was 29.4, and therefore I had a delta T of 7.6 degrees Celsius. And what we're going to do now is use this information, everything so far, to calculate the enthalpy changes. Okay, so for the magnesium oxide, we use 0.9 grams of the magnesium oxide. We'll need that information. We had 50 centimeters cubed of the acid, which is effectively water, so the mass of the water was effectively 50 grams. And delta T was plus 15.6 degrees Celsius. So our first equation, delta E equals M times C times delta T, where M is the mass of the water, which was 50 grams. The specific heat capacity is 4.18, and delta T was 15.6. And that comes out as 3,260.4 joules. Divide that by 1,000, comes out as 3.2604 kilojoules. I'm just leaving that as it is at the moment, I'm not rounding that. We now need to calculate the number of moles of the magnesium oxide that was added. So the number of moles is equal to the mass of the magnesium oxide divided by the molecular mass of the magnesium oxide. So that's your 0.9 grams divided by 40.3, where 40.3 is the molecular mass of the magnesium oxide. There is a separate video on the channel if you're not sure how to calculate that. And that comes out as 0.02233. I'm going to leave it in my calculator though. Okay, so delta H, which is what we want to calculate, is equal to minus delta E over N. So that's minus 3.2604. Divide that by the number of moles, which is the 0.02233, but leave it in the calculator if you can. And when you put that into the calculator, that comes out as minus 146 kilojoules per mole to three significant figures. So it's exothermic, and 146 kilojoules per mole has been released in terms of energy. And what we're going to do on the next slide is repeat that for the magnesium carbonate. So for magnesium carbonate, you used 3.5 grams of the magnesium carbonate. You had the 50 mils of the acid, which is effectively 50 grams of water. And the temperature change was plus 7.6 degrees Celsius. So delta E equals the mass. I'm going to go a bit quicker this time. So that's 50 times 4.18 times 7.6. And that comes out as 1,588.4 joules of energy, which we divide by 1,000, and that is 1.5884 kilojoules of energy. The number of moles is equal to the mass divided by the molecular mass. So the mass was 3.5 grams, and we divide that by the molecular mass of the magnesium carbonate. Which is 84.3. And that comes out as 0.0415 moles. I've rounded that, but keep it in your calculator. Remember that delta H equals minus delta E over N. So that's minus 1.5884 divided by the 0.0415. And that comes out as minus 38.3 kilojoules per mole to three significant figures. But for the purposes of these calculations, I'm just going to call it minus 38. So to bring this all together, let's go back to our Hess cycle that we had at the very beginning. The magnesium oxide plus the carbon dioxide gives magnesium carbonate. But we can't measure it directly, delta HR. But what we can do is add magnesium oxide to acid and magnesium carbonate to acid to give the neutralization products. Where this is arrow 1 and this is arrow 2. And therefore delta HR, what we're trying to find out, is equal to arrow 1 minus arrow 2. Well, arrow 1 was minus 146, and then minus 38, which is the same as adding 38. So it's minus 146 plus 38. And that comes out as an answer of minus 108 kilojoules per mole, which is the answer to the question. Anyway, thank you for taking the time to watch this video. I hope it was helpful. If it was, please like, please share, please subscribe, and keep checking back for more content. See you next time.